So, good evening, everyone, and welcome to the 10th live session of mine for the course Design of Reinforced Concrete Structure offered by NPTEL. I am Harshit Agrawal, a PMRF research scholar from IIT Bombay, and I will be conducting weekly live session throughout the 12 weeks of this course. So what is this live session all about? So these are doubt clearing and interactive sessions that will be conducted every week on Tuesday from 6 p.m. to 8 p.m. till the course runs. How do we interact in this class? By answering to the questions that I will ask in the chat box, posting your queries in the chat box, or by raising hand, unmuting and asking your queries. Apart from the class, you can always use the discussion forum of the course, wherein you can raise your queries, and the questions will be addressed through the discussion forum only or in the next live session. And through these interactive sessions or live sessions, you will be able to answer the graded assignments easily, and it will help you to further understand complex topics holistically. So, what today we will cover? So, in today's live session, we'll first have a recap on what we discussed in the last live session, that was week 9 of this course. Just a quick glance. Then, we'll have an overview of the week 10 content of the course, wherein we'll first see the introduction to reinforced concrete staircase. Then, we'll define different components of staircase, different types of staircase. Then we'll study parameters related to design of a reinforced concrete staircase, and then we'll solve a numerical on design of a reinforced concrete staircase. So this lecture will be comparatively a short lecture, since the topic that we are discussing is not that complicated. So we will have just a simple discussion of staircase and a numerical on it. And finally, we will conclude the week. So just to recap what we learned in week 9 of this live session. So we saw design of slender column. So we know what is slender column, the columns in which the ratio of length to the so in slender column, we understand that when the internal eccentricity also becomes critical in design, so we need to take additional movement into account. So in this figure, you can see, apart from external eccentricity, so we have short columns like this, where ratio of length to the lateral dimension is less than 12. Okay, so in such columns are known as short column. Okay, in this there is only external eccentricity which can generate the moment. But when we talk about slender column, the ratio of length to the lateral dimension is greater than 12, and in such cases, what happens, due to axial load also there is deflection in the column, and this deflection is significant enough to generate an eccentricity which can cause its own moment that is needed to be considered. So we saw how this moment is calculated, and then we did a numerical on it to design a RC slender column with, along with understanding the reinforcement detailing. After that, we saw design of reinforced concrete footings. So first we saw what are RC footings, how RC footings comes into place when the load is transferred from the substructure to the beneath structure, and we saw how the design is interpreted from both two engineering domains, geotechnical engineering and structural engineering point of view. Once we understood the importance of footing, we saw different types of RC footing. So major classification is done based on the ratio, based on the depth of footing and breadth. So if my depth of footing is less than breadth, I say it is a shallow footing, shallow foundation or footing. And if it is greater than breadth, then we say it is a deep foundation. Foundation are combination of footing. So we can say either thing, footing or foundation. Okay. Now, more specific, if we see, there are majorly five types of footings. Isolated footing, that is individual footing beneath a column. Then there are isolated footing with straps, when two isolated footings are connected with a beam like a structure. Then we have combined footing. These takes place when two isolated footings don't have much gap between them, so we combine them to make a combined footing. So it can be like two columns having a single footing like thing. Okay, then we have mat footing. Mat footing is like the whole basement has a single footing, so all columns are here, and we are not providing combined or isolated footing. We are providing a single footing for the whole building, so that is known as mat footing. And then there is pile footing. So when we go for deep foundations, we provide pile footing. So piles are generally circular or rectangular elements that dig deep into the soil. When my upper structure of soil is very weak and I need to go till very beneath the ground or till stone works, then we go for pile footings. Okay. Then we saw different design parameters of RC footing, in which we first saw that how we calculate the dimension of the footing. Then we saw how we estimate the ultimate soil bearing capacity. Once we understood this, we saw what are the minimum criteria of reinforcement and cover. And finally, we saw how we calculate the thickness, required thickness of the footing. So for thickness, we have three criteria. It should be able to resist bending without providing any compression, and it should be able to resist shear without the use of shear reinforcements. So in shear also we saw two things: one way shear and punching shear, and how we choose the critical location where the shear can occur and how we design for it. Everything we understood. And finally we saw one numerical for designing a reinforced concrete footing, isolated reinforced concrete footing. Okay, so I hope the discussion that we did on RC footing and the numerical that we did on slender RC column was clear to everyone. Now, in today's class, we are talking about design of reinforced concrete staircase. So, what are staircase? Staircase are important in any building structure for transportation and communication between the floors in a structure. So, if you see in the images, we know different elements of reinforced concrete structure till now. There are at individual floors we have beams and slabs. For carrying load from one floor to another, or for providing elevation, we have columns. But how we can move from one floor to another, for that we need a adjacent connecting element, which is known as staircase. So staircase, main purpose of staircase is for transportation and communication. And this, in these images you can see different types of staircase. Like one, like more aesthetic staircase. This is more of a journal kind of staircase. This is round staircase. These are more common staircase. So there are different ways in which we can connect two floors of a building, and the that is through staircase. And these are also, this also becomes an important part from design point of view. Why? Because it will also carry load, human load it will carry. So for that also we need to define design it for safety. Okay. Now, what are the basic components of staircase? When we are talking about designing, we first need to we should first understand what are the basic components that are present in staircase that we need to remember while designing. So the first, these two are the major components. Okay, thread and riser. So what is thread? Thread is the horizontal portion or step over which the foot is placed during ascending or descending a staircase. So if you can see in this image, this part is the thread. Okay, the place where we play, the portion where we place our steps. Okay, so this is tread. Riser. Riser is the vertical member of a step which is used to connect successive treads. So this length, this height of a step is known as riser, which helps us to connect two threads. Okay, this is known as riser. Okay, flight. Series of step provided in between landing. So this is known as landing. Landing is the area where we can take rest. Okay, so this is one landing, this is second landing, and this is third landing. So these two landings are basically floors: ground floor, first floor, and this is in between those floors. So between two landings, how many flights, how many steps are there? That is known as flight. Okay, headroom, the vertical distance between tread of one step and ceiling of the overhead construction. So suppose this is my roof. Okay, and these are my steps that are coming. Okay, so headroom is the distance between the step and the roof of that building. Okay, so that is the distance, vertical distance between the tread of one step and the ceiling. This is the ceiling of that floor. Okay. Stranger, sloping element of a staircase which is used to support the end of the staircase. So in this image, you can see this is stringer. Stringer can be basically a slab. You can consider it as a slab over which these steps are placed, which helps us to carry load. So in this, you can also see this is the stringer. Okay, this part. this slab like thing, na, this is known as stringer. Okay. Winders, so steps that are used for changing direction. So if I go in the previous slide, so when we have circular steps, these steps are known as winder. Okay, which are not rectangular in shape but more of a triangular in shape, so these steps are known as winders. Okay, landings, the horizontal platform provided at the head of each step as a resting place. So this is the landing that we talked. Okay, in between steps it can be there, or just in between floors it can be there. Nosing, so nosing and going are the part of thread only. So if we see, suppose sometimes I have such steps. Okay, so in this step, the portion till here is known as going, and this is known as nosing. Okay, so you can see here also the projecting part of a thread belong the face of the riser. So this is my face of the riser. The part beyond that is known as nosing, and the part before that is known as going. Okay, so these are the main terminologies that are associated or main components of a staircase that one must know while designing. Now, based on these things, there are basically majorly three types of staircase: straight staircase, dog leg staircase, and circular staircase. So, what are straight staircase? When two floors are connected by a single go. Okay, so you can see there is a single flight. We talked about flight, na? The series of steps between two landings. So, my first landing is the ground floor, my second landing is the first floor. So in between them I have a single flight in which I am moving, so that such cases are known as straight staircase. Dog like staircase, when there is landing in between. So you see this case was a dog like staircase. When you are not moving from one floor to another floor in a single blow, you have two flights here, or maybe three, or maybe four. So in such stairs are known as dog leg staircase. And another one category is the circular staircase, in which we have, along with simple tread and riser, we also have winders, which are placed in between, and they are more aesthetic in appearance for connecting two floors. So they are like in between dog legged and straight staircase, we can say. But for simplicity of discussion and design, today we will discuss how to design a straight staircase. Okay, from straight you can always design a dog leg staircase, just you need to distribute the flight. Okay, so today we'll see how this straight staircase is designed. Okay, now what are these parameters? How are these parameters defined when I talk about design of staircase? So we saw tread, the horizontal part. So for factories and dwelling houses, the code says that tread should be at least 250 mm, IS 456, according to IS 456. Okay. So these are some minimum values that you need to provide. Suppose you have a project in which it is said that you have a ground floor and the first floor, and you need to design a staircase. So the tread, the riser, how to choose them? You need to have a base using which you can design those steps. So for tread, if you are designing for factories or dwelling houses, your tread should be at least 250 mm, and for public buildings, your tread should be 270 mm. Okay. Similarly, riser for factories, it is generally taken as 190 mm. For public building, it is taken as 150 mm, and for residential buildings, it is taken as 160 mm. How this value came up? Based on like convenience. Okay, you can't have a very long riser, it will make your movement inappropriate, or very small riser also, it will make your movement inappropriate. So these values are generally picked. And if you are not able to choose tread or riser specifically, so you always need to go with this formula. So 2 times r plus g should be less than 700 or greater than 550. So my r is the riser and my g is the going. You saw here going, we saw here going, that, like, if this is my step, okay, this part is my going. Okay, so whatever value you are choosing for tread and riser, it should satisfy this equation. Okay, then only we'll say that your design is convenient for use. Okay, so these are the criteria for tread and riser. Next is for headroom. Headroom, we saw what is it? The vertical distance between the roof and the step or the riser of a step. So minimum vertical headroom above any step should be 2 meter. Why? So that it is convenient for movement. So suppose this is my last step. Okay, these are my series of step and this is my ceiling. So this distance between the last step and the ceiling should be at least 2 meter. Okay, so you need to design your steps accordingly. How many flights you need to provide, you need to choose such that that distance is at least 2 meter. Okay, flight. Number of risers in a flight should be restricted to 12. So if you are connected two floors and you're designing steps between them, so number of steps between in a flight should not be greater than 12. Okay, this is basically based on convenience. Okay, width of the step. So what is like if I see a top view, so this will be my step. Okay, so you see from side view we see like this. Okay, this is my length and this is my height. So I'm talking right now talking about the width. Okay, so minimum width of a stairs should be 850 mm, though it is desirable to have a width between 1.1 to 1.6 meter. Okay, so this is some criteria that also you need to follow when you are designing the width of the stair. Okay, and the last thing based on the parameters like dimensions of design is the effective span. So what clause 33.1 says of IS 456, there can be two cases. This is my supporting beam which supports a staircase. Okay, so my supporting beam can be either at a distance y and xx from the step or just below and above the step. So how I define the effective span? Why I need the effective span first for designing this slab thing. Okay, for designing a staircase, I need the effective span. And how I get that effective span? Based on these two cases. So if I am belonging to case one, if the supporting beams of the steps are located at some distance from the step, and if this value, this total is suppose 2y. Okay, so this is y and this is y. Okay, and this total is also 2x. So I will say this is x and this is x. Okay. So if my x and y is less than 1, then my effective span is given by x plus y plus going length. So going length is the total going length of each step. Okay. And if my x and y are greater than 1, my effective span will be taken as 1 plus 1 plus going length. Okay. So effective span should not be greater than going length plus 2 if I belong to case 1. And if I belong to case 2, my effective span will be the center to center distance between the beam. Okay, so these are supporting beam. The center to center distance between the supporting beam is my effective length. Okay, so effective span. Okay. So these all these criterias that code defined were related to the dimension. Now, what about loading? How to take loading into account? So as per IS 456, for residential building without overcrowding, we take live load as 2 kilonewton per meter square while designing, and for public buildings where overcrowding can happen, we take live load as 5 kilonewton per meter square. So this is generally what we consider when we are designing a staircase. And what about dead load? So if you see, this is my step, and below the step I have my slab. Okay, so same figure is here also. So this portion is my slab step. Okay, and below that this is slab. Okay, so how I can calculate the dead load? So per meter square of an horizontal span. So we know this is like step is like this. Okay, so if I consider 1 meter span of this step, so what will be the dead load? The weight of the rectangular slab, the weight of this slab plus weight of this triangular portion. So how we calculate that? So suppose my width of the slab is w, my rise is t, riser height is r, and my total thread length is t and my going length is g. Okay, so my b will be nothing but from Pythagoras theorem I can calculate it is under root of r square plus g square, this length. Okay, and so dead load per meter square, what it will be? W times b into 25 kilonewton per meter square, which is generally what we consider the kg per meter cube that we consider as a density of concrete divided by g, it will give me kilonewton. Weight, like mass to weight, for converting mass to weight I have divided by g. Okay, so w times b times this will give me the weight of the slab, and half half into breadth into height is my area of the triangle, so multiplied by this it will give me the weight of the triangular portion or the step. Okay, so this will be total my dead load per meter square of an horizontal span. Okay, so I have considered this as 1 meter. So according for that, for per meter width, this will be my dead load, kilonewton per meter width. Okay, so this is how we calculate the dead load. Now, once we have the dead load, everything, how we can do? Now we can design. So we know the loads, we know the dimensions. So we can calculate what is the moment that is acting. So we can design. So since it is a slab, okay. So if we consider this as a one-way slab, and I know what is the load acting on the slab and what is the dimension of the slab, I can design for reinforcement, the additional reinforcement, and everything. So this chart shows you that basic layout of basic flowchart of a design of a staircase. So first step is to choose the effective span. We can calculate the effective span based on the location of supporting beam. Then we'll choose a trial depth. So like we do in one way slab, na, we have an L by D ratio less than 20, less than 25. So initially, once we know the effective length, what we do, we choose a trial depth. So taking any of these value, will take a trial depth. Suppose I choose L by D ratio as 30. So using this, I will get a effective depth, trial effective depth. Now based on that, I will calculate the total depth, and then I will calculate the load. Load calculation I will do, which is nothing but dead load plus if any finish is applied on the uh, steps, that load and the live load. Once load calculation is done, I can calculate the design moment. So for this, I can calculate the design moment. I know the length, I know the weight, so I can calculate the design moment. Once I know the moment, I can calculate the tensile reinforcement. How? Under root of 0.136 0.138 fck bd square, like that moment, if it is less than mu, I will say it is like singly reinforced section. And then using the relationships that we discussed in the design of beam, first calculating the x by d. Once we get the x, we can calculate the ast, so we'll get the ast value. Once I know the ast value, what I will do, I will check for reinforcement, minimum reinforcement, if it is provided or not. So in slab we know minimum 0.12% or 0.15% of reinforcement that we need to provide. We will check for that, and then we'll check for depth. So I, from once I know the reinforcement, I can calculate the modification factor, and then I will check whether my L by D that I have provided is less than what was actually assumed or not. If it is true, then I will say that my design is correct. And once it is done, I will provide the distribution steel. So we know in one way slab, we provide distribution along only one direction. So we just need to provide some distribution steel also along other directions, which can resist any shear if it is happening or not. So this is how we design a staircase. So just what difference it is making from the design of slab, just that load calculation and the initial choice of effective span. Once that is done, everything is the same. If you have chosen the number of flights, the width and the height of steps, after that everything is like a design of slab only. Okay, so based on the theory, based on everything that we have discussed till now, we will do one numerical. Okay, so what this numerical says: design one of the flights of a staircase of a school building spanning between landing beams to suit the following data. So type of stair is a waist slab staircase. Number of steps in flight is 12. Thread is given as 300. Riser is given as 160 mm. Width of landing beam is given as 400 mm. Materials M20 grade concrete and HYSD Fe415 grade steel is what is it is given to us for use. Okay, so I will wait for like 5 minutes. Try to like first picturize how this step would be looking. Try to do the load calculation and everything, and then we'll solve the question. I will be on mute for 5 minutes. Okay, so let's see the solution now. So first, what all things are given in the question? Okay, so given uh, number of steps, 12 steps there are. Okay, T is 300 mm, R is 160 mm, width of landing beam is 400 mm, and we need to use M20 grade concrete and Fe415 grade steel. Okay, so this all things are given to us in the question, and one more thing that is given to us in the question is that which how we can calculate the effective length. So since it is given spanning between the landing beams, since so it is like this case. My landing beams are here at the top and the bottom of the staircase. Okay, suppose this is my staircase, so like this. So my effective length, effective span will be the center to center distance between the beam. Okay, so this will be my effective span. How I can calculate this? So I will take a new slide, just removing this part. So this is the data that I know. So step 1 is calculating effective length. So my effective length will be the center to center distance between the beams. So what is my width of landing beam? So 400 by 2 plus what is the total going length? So number of steps are 12 and tread is 300. So 12 times 300 plus again 400 by 2. So this will come out to be 4000 mm. Okay, so this is the width of effective span. Now step 2 is to, what is the step 2? To take a trial depth of underneath step. Trial depth of underneath slab. So let's assume I am taking L by D ratio as 20. Okay, let's say 20 will be sufficient for me in this case. So from this I will get my effective depth as L by 20, which is nothing but 4000 mm upon 20. So it is 200 mm. So 200 mm is my effective depth of the slab. Okay, the waste slab that is there beneath. Okay, so I'm assuming I'm providing a 200 mm effective depth. So if I take a clear cover of 20 mm and suppose I'm using 12 mm diameter 3 bars. So my total depth will be 200 plus 6 plus 20, so it will be 226. I can say 230 mm. Suppose I am providing, assume. Okay, so my effective depth will be something 204 mm. Okay, in this case, since my total depth is something that we design for, so it should be a whole number. It should not be like 226. It would be inappropriate to like design for 226. So generally we backtrack that thing. Okay, so my this length I am providing as 230 mm total depth. So my effective depth will become now 204. Okay, small d will become 204 mm. Okay, now what is the third step? Third step is the load calculation. Since there is no floor finish or anything given, we will assume it right now. for now. So step 3 is load calculation. Now how to do this? So what was our formula? So since it is a school building, it is a public building, my live load will be 5 kilonewton. Okay. Need to design a staircase public building. Okay. So my live load will be equal to 5 kilonewton per meter square. Okay. My dead load, how I will calculate the dead load? So dead load will be nothing but using this formula. Okay, WB plus half RT into 25 by G. So WB plus zero point 0.5 times RT into 25 by G. Okay, so how I will get this value? So W I know. So B we need to calculate under root R square by G. W, that is what we designed for the width of the slab, the total depth of the slab. Okay, so that is nothing but 230 times B. The length is nothing but under root of R square plus G square. So my rise is given uh, 160 and that is given 300. So under root of 160 square plus 300 square. Just let me do the calculation. So it will come out to be 340. B will come out to be 340 plus zero point 0.5 times RT. So what is my R? 160 times my T is 300. Okay, whole into 25 by G. So here G is my going. Just let me clarify once. 25 kilonewton per meter cube. So this is 25 kilonewton per meter cube only and G is the going. So we are calculating per meter with, okay, kilonewton per meter na, so this will give me kilonewton per meter width. Okay, so this is going. Okay, G, the going length, that G and G are same, so that is nothing but 300 again. So upon doing this calculation you will get, I hope I am audible. Yeah, so we'll get 230 into 340 plus zero point 0.5 into 160 into 300 into 25 divided by 300. So it will come out to be 8.52 kilonewton per meter. Okay, so this is my dead load. Now next is per meter width we are calculating. So we can write like this. Live load I know, dead load I know, and I can also calculate the floor finish. So suppose I am taking a floor finish of, let's say, zero point 0.6 kilonewton per meter I am taking. You can take also, you can't take, you, if you want, if you don't want to take, you can ignore, but I am taking. So total load is 5 plus 8.52 plus zero point 0.6, so it will come out to be, it will come out to be 14.12 kilonewton per meter. Okay, so this is my total, but it is not the factored load. So total factored load will be 1.5 times this. So 1.5 times 14.12. So it will come out to be 21.18 kilonewton per meter. So this is how we do the load calculation. Okay, so we know the ultimate load now. Okay, this is the ultimate load. Now what is the next step? So I will remove all this part. So once I have done the load calculation, my next step is to calculate the design moment. So step 4, I guess. Yeah. Step 4 is calculating design moment. So mu is nothing but 0.125 W L square. Okay, so I know W also, I know L square also. So it is 0.14125 W 21.18 into L square. So L length is my effective span, which is 4 meters. So 4000 into 4000. So this will come out to be roughly around 40 kilonewton meter. Okay, just let me check once. 42.336 kilonewton meter. Okay, so this is the moment that for which I need to design. Now step 5. Step 5, we will check for depth. Okay, whether the depth that we have provided is sufficient or not. How we will check? Based on mu limiting. Based on mu limiting, we can check this depth. Okay, just wait a second. Okay, so for Fe415 steel, mu limiting is nothing but under root of 0.138 FCK dd square. Okay, suppose if this is my mu limiting, the mu that I have calculated, what will be my d? Okay, so this value is 42.36 kilonewton meter. Okay, so I can backtrack and calculate the d small d. Okay, so my small d will come out to be, just let me do the calculation once. What is the b? B is 1 meter. Okay, per meter width we are defining, right? So 52.53. So 42.36 into 1000 into 1000 divided by 52.56. Okay, just let me do the calculation here only. I'm confusing. 42.36 into 1000 into 1000 divided by 0.138 divided by 20 divided by 1000 and this under root. So copy under root. So its small d will come out to be 123.89 mm, which is less than what we have provided. What is the small d that we have provided? It is 200 mm, 204 mm. So we are safe in this case. Okay, so this is how we check. Okay, so effective depth that we have provided is greater than the required depth. So we can say effective depth that we have provided is greater than required effective depth. Okay, so we are safe to go ahead. Okay, now this was step 5. Step 6 will be to calculate tensile reinforcements to be provided. Okay, so how we'll do that calculation? So once we know the effective depth and we know what movement we need to resist for, and we know the width per meter width and grade of steel and concrete, so we can directly use the in the design of beam how we saw a relation. Mu is nothing but 0.87 Fy AST D times 1 minus AST times Fy upon BDFCK. BDFCK. So using this relationship, we can calculate the AST. We know mu is equal to 42.36 kilonewton meter. Fy is 415 Newton per mm square. FCK is 20 Newton per mm square. D is 1000 mm and small d is 204 mm. Okay, so substituting this relationship, or you can also use table 2 of SP16. Okay, that is also an alternative if you want to use. So where how there what you need to do, you need to calculate just mu by bd square and percentage area of steel you will get. Okay, suitable percentage area of steel you can get from that. Okay, so right now I have the final value, so your AST will come out to be around 696 mm square. Okay, so for this, since I am providing 12 mm rebars, okay, so I need to calculate spacing. So how I will calculate spacing will be nothing but diameter area of one rebar upon total area into 1000 per meter width, how many we need to provide. So from this you will get a spacing of 160 mm. Okay, so we will provide 12 mm diameter rebars at the rate 160 mm center to center as main reinforcement. Okay, so this is how we design for tensile reinforcement. And what about distribution steel? Since this is a one-way slab, we need to also provide distribution steel. So what is distribution steel? The minimum reinforcement, which is nothing but 0.12% of BD. So 0.12% of B is my 204 times 1000. So it will come out to be roughly around 240, or I will say 248 mm square per meter. Okay, this is per meter, I won't write per meter, so you can understand we are designing per meter. So for this you can provide 8 mm diameter reinforcement. You can assume the reinforcement dia that you want to provide. So I am assuming 8 mm diameter reinforcement. I will provide it at a spacing of 200 mm center to center. Okay, center to center. This will give me an AST of 250, which is more than what I require. Okay, so this is how we calculate the reinforcement. Now once we know the reinforcement, we can always check the check for deflection. We can do, we know the length and we know the effective depth, so you can always do the check for deflection. Okay, so this is basically how we design. And finally, if you want to like make a figure also for design, so I will just show you one example of it. Okay, so I know all the points. So this is my like floor, this is my supporting beam, okay, and this is my staircase. Here again I will have a beam, and this again will continue the floor. From here my steps will begin. Okay, okay, so this is like a rough diagram, you can understand. So I know this height, rise, I know the tread or going, both are the same, and I know how much reinforcement I need to provide along this direction. This is the main reinforcement. Okay, so this main reinforcement is 12 mm dia bar at a spacing of 160 mm. Okay, and above this I will have distribution reinforcement. Okay, that I will show in terms of points. So this will be my distribution reinforcement, which is nothing but 8 mm diameter bars at a spacing of 200 mm. Okay, so both are clear to me. And this is enough. I know the width of the landing beams, I know the reinforcement, and I know number of steps that I need to provide and the thread and the rise. So this is how finally you draw. This drawing is not that proper, but you can understand how we design. Okay. I hope the question is clear to everyone. Any doubts in the question? Any doubt in any of the step? Yes, say. Nikhilesh, do you have any doubt? Okay, so this was all about this week. This week, the discussion was very small. Okay, since we need to just understand the design of staircase and we can't move into very complex design. Why? Because design of circular staircase and all are not the part of this course, that are more specific to staircase design. And right now we are just understanding how different elements of a reinforced concrete are designed. So for that I choose a very simple question for now, that is design of a straight staircase. Maybe in the next class I will try to bring up a question on dogleg staircase if possible, but you can understand the essence of design. So the essence of design is to follow these flow chart, where first you need to choose the effective span, then you need to calculate the, you need to choose a trial depth, then you will do load calculation, then you will calculate design movement, then you will calculate tensile reinforcement, you will check with minimum reinforcement if it is true or not, and depth if it is true or not. Once that is done, you will provide the distribution steel and you will make the design chart. So that is what we did in this question. Okay, so, just to conclude the week, we started the discussion with understanding the role of staircase. Then we talked about design terminologies associated with the staircase design and major types of staircase. So, what were those terminology? Tread, riser, flight, and everything that we talked. And major types of staircase were straight, dog-legged, and circular. Then we understood different parameters related to staircase design and what IS 456 says regarding them. So we understood what are the different limits that IS code provides that we need to take into consideration when we are designing a staircase. And finally, we solved a numerical on design of a RC waste slab staircase. Okay, so this was all for like this week. Any doubts in the discussion today? Okay, so if there are no doubts, you can like leave the meeting. The class is over. Okay, thanks.